acceleration of an object depends on the mass of an object and the amount of force applied.
Yes?
And then when two objects interact, they experience equal but opposite.
Good. 1. We, as Trey correctly said, an object in motion will stay in motion unless acted upon by an outside force. There's another part of that. I mean, almost like a corollary. There's another side to that. What is it? He said if an object is in motion, which is correct, it will stay in motion unless acted upon by an outside force. What's the other part of that?
Are you looking for the first one, right?
Mm-hmm. I forgot to say it's science time. I'm so sorry.
What? Oh.
It's science time.
Oh,
It's science time. That's right. Close your laptop. It's science time. We don't use laptops in science.
unless acted on by an unbalanced force.
Okay, yeah, and that's what I should have said is unbalanced force, but that's still not quite the thing I was asking for. Again, Trey said, an object in motion stays in motion unless acted upon by an unbalanced force. And that's true. It's not the whole truth. What's the other part of that whole truth? Avery, I choose you. Yeah, okay. So an object in motion, I'm going to do it. Actually, I'm going to do it like this. This will be nice and confusing. In motion or at rest. I'll just make it put a little. An object in motion or at rest will stay in motion or at rest. Unless, ooh, fancy unless. Unless what?
Acted upon by an outside force.
Yeah, it does. I think even in Newton wrote it in Latin, but in the original, I think he does say outside force, but we want to be specific and say an unbalanced force. Because we had talked about force, net force. Remember net force when we add all the forces on an object up together? We had talked about that before, and so we already know what unbalanced means to us. Is that in picture now, Tiana? Just peek your little head around there. Like it's got a little one and a big one. Okay. So an object in motion or at rest will stay in motion or at rest. And you know these things go together. If it is in motion, it stays in motion. If it is at rest, it stays at rest. Unless acted upon by an unbalanced force. So whatever it is doing, it keeps doing. Unless. Okay? This can be summarized in one word. Does any of you very smart 8th grade cookies know what that one word is? It is a Latin word. We use it in English too, but the word comes from the Latin. You might have read it in your explorations.
Inertia?
It is. Who said that? Great work, Ramrock. Remind me. Inertia. Inertia is the Latin word for laziness or sloth. In the list of the 7 deadly sins in Latin, one of them is inertia, to be lazy. But in physics, we use it to mean exactly this, that if an object is still, it will remain still unless acted upon by an unbalanced force. Or if an object is moving, it will continue that exact same motion, which is a straight line at a constant speed. Does that ring a bell to you? Do you remember another time we talked about straight line and a constant speed? Acceleration, right. These are the two ways an object is not accelerating. Remember, at rest or straight line constant speed. So another way of saying this is that an object with no unbalanced force acting on it does not accelerate. Right, inertia means no unbalanced force, no acceleration, which brings us to number 2, which is what? Say it in your words again, Trey. I like the way you said it earlier. Look, now it's like a crazy person did. I got arrows going all over the place like the classic crazy guy in the Crazy People movies. Let me mess my hair up a little bit more too, and then it'll really sell it. Acceleration, which redefine acceleration for me. We've talked about this at least twice. I mean, we've done 2 videos about this. Define acceleration for me. I appreciate you taking your time to actually think about the right answer and not just, thank you. Who said change in motion first? Good job. Change in motion. Someone, can't tell if it's a boy or a girl, said like going faster. And that's true too. That's one type of change in motion. That's one type of change in motion. But remember, any change in motion is acceleration. So could it be going faster? Yes. That's how we and the police and the truck drivers use it. But it could also be slowing down, and to the physicist, that is acceleration. The police and the truck driver might call that deceleration, but to a physicist, it's all change in motion. And what's the other one that people always forget? You remember?
Turning.
Turning, yeah, changing direction. Because velocity includes direction, and so change in motion, change in velocity is also turning, or could also be turning. And that depends on mass, and why did I link with my Crazy People line here? Mass and an object. Yeah, it's a mass of an object, and all objects have mass. That's the definition that we use in science of matter. There's more stuff that matters than just matter, right? Like light and energy and love and gravity. Those things all matter, but they are not matter. Do you know what I mean by that? I'm making kind of like a poetic joke, but do you know what I mean by matter? And I'm like kind of like conflating the way we use the word matter and what we mean in science by matter. Matter is anything in science that has mass and takes up space. So any object will have mass, and its acceleration will depend on that and the force applied to it, which must be, in order for there to be an acceleration, that force must be unbalanced. Look, we can get another arrow. Must be unbalanced. There's math with this one. We'll do it more next year, but the math, it's actually pretty easy, but it's just F equals ma. Force equals mass times acceleration. There might be a little bit of something like this on your test, but you won't be held to the same mathematical standard as you will be next year. Next year, we kind of do all of this stuff that we're talking about now in this part of the school year again, except with math, which is nice because you already know these words, hopefully by then. And then we'll just add math next year. Add math. That's a cute thing to say. And then the third one was what? Yeah.
For every action, there's an opposite reaction.
Yeah, this one is, for a lot of people, the easiest one to remember. For every action, there is an equal and opposite reaction. Why did he capitalize reaction? I don't know. And also it's kind of going, whatever. For every action, there is an equal and opposite reaction. I don't like this one. The way that you said it good, and this is how people remember it, and I like that it has kind of a rhythm that makes it easier to remember, but I much prefer this word interaction, because action and reaction make it sound like one happens first and then the other one occurs. But they go together. They're always together. It is one of the most basic laws of physics. Well, these are the most basic laws of physics. But one of the most basic laws of physics is that these things go together. It's not... I'm trying to think of an example that isn't specific students punching each other in the eye. What was the other? If you... yeah, I know, but I'm trying not to say their names. I'm trying not to say their names. We'll say Riston and Taven, and if Riston punches Taven, it's not that he punches him and then his head hits his hand. It's the same thing. That same motion causes both the punch and the re-punch, right? The classic example is if I push this wall, it pushes back, right? How can you tell? I'm pushing on the wall with a lot of my weight. How can you tell it's pushing back? Because someone will raise your hand. Justine. Yeah, both me and the wall's supporting me, right? It's if I did that with the air, I can't because of I'll fall down. But this action, me pushing, is not followed by the wall pushing me back. They are the same thing. Me pushing the wall is the wall pushing me. Riston punching Taven doesn't result in Taven hitting Riston with his head. They are the same interaction, right? Do you see what I mean? It's an interaction. They go between, they interact. Yeah, good. Thank you for protecting people's identities. You mean that in the fight, then the next thing that happens is he headbutts him. Sure, but that's a whole different thing. That's not the laws of physics. Now, that's the laws of social economics. Hush, please. So it's an interaction. It's the same exact happening, just from two different perspectives. The real easy way to do these is you kick ball, ball kicks you, right? It's just the reverse. It's almost like a chiastic structure. It's almost like a chiasm. It's you kick ball, ball kicks you. You hit wall, wall hits you. That's why you feel it, right? I'm sorry, dinosaur. I caused a dinosaur to fall down. More or counterintuitively, you jump off building and Earth pulls you, but remember we talked about this last time. What's the reaction? No, come on, just say it. Just say it. You kick ball, ball kicks you. Earth pulls you, you pull Earth. But why don't we notice, right? We do notice the acceleration of this guy, but we don't notice the acceleration of planet Earth. Why? Because Earth has a big mass and therefore a little baby acceleration, and you have a little baby mass and a big acceleration, right? Because both of these have the same F. Because F equals ma. Right, let's do some real quick math. Let's say with a force of 100 newtons, your 100 kilograms is pulled with an acceleration then, oh sorry, I did it the wrong way. Yeah, I guess this will work. An acceleration of 1 meter per second squared. But Earth's mass, it's still a force of 100 newtons, but Earth's mass is 10.
Wow. Dang.
It has to be 24. 1, 3, 6, 9, 12, 15, 18, 21, 24. That's roughly correct. So this is the Earth's mass. So what will its acceleration be? Well, 0.00000000001. It has a little baby acceleration. Does that math kind of make sense? This is how we do the math with F equals ma. But since the Earth's mass is big, its acceleration is very, very small. Immeasurably small. And since your mass is relatively little, also P.S., no one in here has a mass of 100 kilograms. But since your mass is relatively small, you accelerate at this much. It should actually be this much on planet Earth. So these really should be 1,000 newtons. But the math, this is trying to demonstrate to you that even though it doesn't seem like it makes sense, it doesn't make intuitive sense, it doesn't feel right, when the Earth pulls you, you pull the Earth. It's the law of physics. It's the law of physics. Whether or not you understand that or agree with it, could you answer a question correctly about that? The question is, do you pull the Earth when you fall? Mm-hmm. How could we test this? Yeah, okay. Yeah, so if we got every person on one side of the globe and jumped at one time, it probably would not actually measurably move the Earth, even still. But scale it up even bigger. It doesn't have to be people. What else could it be? No. No. Think of something even bigger. It doesn't have to be people. Okay, so even bigger than a meteor.
Jupiter.
Who said the moon? You get a Ramrock moon. It's a good job, Avery. The moon. Does the moon influence the Earth's acceleration? Yeah, that's what we call the tides. There's more to it than just the tides. But the moon, which is smaller than Earth, right? But still, it's bigger than a person. I don't know if you know this about the moon. Other than your mom, it is bigger than a person. And that gravitational interaction is actually observable. The acceleration there is observable. because the moon pulls on the Earth just like the Earth pulls on the moon. You pull on the Earth just like the Earth pulls on you. When Newton sat under the tree and the apple fell on him, the reason that kind of apocryphal story is told is that Newton thought, why does the apple fall but the moon doesn't? He was working with the idea of gravity and how all things fall, and he thought, why does the apple fall but the moon doesn't? Does anyone know the answer to that question? Here's Newton. Here's Newton's apple tree. The apple falls and the moon doesn't. Or does it? Okay, well, it's not to scale. The drawing is not to scale. The apple falls. What do we agree is falls? Which direction is falls? Down. So the apple falls down. It's stopped by his head. But the apple does fall down towards the center. Is the moon pulled down? Yeah, it actually is. I'll tell you why. Imagine. Oh, hey, Chan, would you get me my wiffle ball with the ribbon on it out of the top drawer of my desk? Imagine a wiffle ball on a string, if you will, for a second, because also I'm going to show you so you don't have to imagine a wiffle ball on a string. It's in there somewhere. Just rummage around. I don't keep a very tight ship in my desk. Okay, so here I have wiffle ball on a string. Right? What happens? Okay, first of all, what force is the string representing in my analogy? Can you guess? Gravity. So you see it? What happens if I let go of the string? Okay, so what could that mean if the string is representing the force of gravity? What could that mean if I let go of the string? In my analogy. Okay, yeah. So if the Earth disappears, whoop, just like the ball going in a circle, if I let go, you should have unducked. If I let go, it goes off how? In what way does it go off? In a straight line. Because Newton's first law says any object with no force goes in a straight line at a constant speed or is at rest. The moon, without the presence of the Earth, would go off in a straight line. How long? Forever, unless an unbalanced force. But so that tells us that since I'm going to put the Earth back, since the Earth is here, what must there be between these? It's making it not go in a straight line at a constant speed forever. Because it actually goes like this, right? It actually goes in a circle. So what force must be acting on it? Gravity. And it's pulling it towards the center. This is the force of gravity. And that is how Newton came up with all of this. Okay, so it does. Now check it out. Good, excellent question, Aiden. So it has its own velocity here, right? It has a velocity, just like the ball when it flies away. But it also has a force pulling it inward. And so at every single second that goes by, it does the average of these. It doesn't fall in because it has a velocity, and it doesn't fly off because it has a force in. And so instead it goes this way, and now it's here. And now it wants to go this way, but it's pulled this way. So instead it goes here. Now it wants to go this way, but instead it's pulled this way, and so it goes here. And guess what? Eventually, it's in a circle, and that's an orbit. So it does fall. The answer is the moon does fall. It's just going fast enough that it misses all the time. Month after month, year after year, millennium after millennium, the Earth and the moon are constantly falling into each other, but they always miss. You guys know about that in your little junior high dance, probably. You're always falling in love with each other, but missing. Bye!